All right, recording is rolling. Welcome to another fine week. It is Monday, August 21st. So what we're going to do is we have a couple things from last week, dimensional analysis, a little bit of algebra, but I really want to get the ball rolling on trigonometry, vectors, vector components. You guys have a page on your desk that looks about like this, and then this on the other side has a bunch of trigonometry stuff. Plus minus a little bit. It's a little bit different versions of that floating around. Get to that towards closer to the end. You guys have your notebooks out. You guys have been solving these while I've been doing attendance. Oh, can you guys bring your laptops tomorrow? Right, I want to do a Kahoot with you guys based on some stuff we do today. There's some other stuff I want to do, but we'll see if we get there. Start few linear motion type notes on Wednesday. Give you guys a lab Thursday, Friday. Next week, linear motion. The week after, projectiles. Please, it's my about a 3-week plan. I'll see how close we can stick to that. All right, so first thing, first. All right, first thing I want to throw up here before I forget, because I didn't write here, is, well, actually, just a couple of things. Still got these name forms. If you haven't turned this in yet, I am going to make return folders for you guys soon. And if you want me to write a name on your return so I can return papers back to you guys that does not match your legal name, then just make sure you get one of these to me. And the other thing I didn't write on here, I want to make sure I grab is this dimensional analysis question. So this is a challenge question, it's mostly for my AP kids, but it's used to you guys too. Okay. So suppose they give you like an energy demand. Let's just run with this number: 25,000 terawatt hours per year for all the states. I say, well, if you wanted to meet that demand with nothing but solar, how much land area would it take? Okay. I told you maximum solar flux, average solar flux, like how concentrated solar coming in. Okay. I also gave you guys an efficiency on those solar panels. So let's walk through this step by step. Before we really answer, did anybody solve this yet? Anybody solve this? Okay. I know so many students did by Friday last week. So awesome if you did or if you tackled it. So let's start with this given value, 25,000 terawatt hours per year. Okay. Now that capital T tera. Oh yeah, go ahead. Yeah, go ahead. Green pass right here. Do you guys remember what capital T tera is? That's 10 to the power of what? A trillion. Yeah, that is 10 to the 12 is a trillion. Ooh, bunch of T words. Tera, 10, 12, trillion. Waha. So takes care of that T, right? Let's reconcile these two time units. You guys see hours here and years here? Can you guys reconcile hours and years? How many hours in a day? Okay, does the number 24 on this railroad tracks that I'm setting up, does the number 24 go on top or on bottom? I'm going to say the top. 24 hours in a day. I'm going to say the bottom. Yeah. You're right. Right. Because here's why. So the number 24 is attached to the unit hours, and this hours and this hours are set up to cancel out. Right. So now I got days up here. I got days up here and years down here. Now that's one step away from reconciling. Days in a year, how many? 365, let's call it. Does the number 365 go on top or on bottom? I'm going to say the top. I'm going to say the bottom. Look at all my, I'm getting more winners. You guys are learning. Yes. Look at that. 365 days in a year. Now days and days. Years and years. Right. So now a bunch of units just went away. At this point of the problem, we have some number of watts. You guys know if you plug in like a 40-watt light bulb, right, it's constantly pulling 40 watts. That's like 40 joules per second. That's a power unit. It's like a rate of energy. Right? So like if the states were just constantly drawing some power, then that's what this part of the table shows. But we don't want that exactly. We want land area. We need to know how much land to buy in Arizona so we can set up some solar panels. Right. Do you guys see a way to convert from land area, or sorry, from watts, like power in watts to land area in square meters? Maybe one of these guys. Now, do we want to be using maximum flux or average flux? What makes more sense? Average? What you guys say an average? All right, winners. Oh, this is a sharp class. I was going to ask you guys, should the number 400 go on top or bottom? But you guys would have said the bottom so that the watts that's attached to cancels out with these watts here. And now, at this point in the problem, all the units have canceled out if you kept track, except for square meters. So we sort of are getting an answer formulated at this point, but how many square meters that is, that's a giant number of square meters. Maybe it'd make more sense to have like square kilometers. Do you guys think? You guys remember that cube over there for scaling? Right. guys, land area, that's a two-dimensional concept, right? So I know there are 1,000 meters in a kilometer, but I'm gonna double that step. It's like a square that step. Right. You guys see these square meters? Can I cancel out with these square meters? And now I got square kilometers. Right? So another way to say that is there are a million square meters in a square kilometer. Yeah. Yeah, go ahead. Green pass right there. Yeah, sure. Pass it off like a football. Now there's one last curveball here at the end. Our solar panels are not 100% efficient. Right? So you guys thinking deep about this? Like if I stop the problem right here, I would get some land area. It's not this number down here. It's like some different number of square kilometers. Right? I'll get some land area. If every watt that hit the panels was useful on the grid, but it's not. Less than 100% efficient are these panels. Does that mean we want more land area or less land area than is shown so far, like revealed? More. We need more land area because these panels are less than 100% efficient. Okay. That tells you something about what to do with this 20% number. Because 20% as a decimal, how would you write that? 0.20. Yeah. 0.20, right? Now, in this railroad tracks, do you want the 0.20 on top or on bottom? We need more land area. Get that by multiplying or dividing by 0.2. Dividing, right? Because if you multiply by 0.2, then shrink down the land area. No, that's the wrong way, right? If you divide by 0.2, doesn't that blow it up bigger? Right. So that's the same thing as multiplying by 5, right? Same thing. Divide by 0.2, multiply by 5, right? One last little tidbit here. So, okay, you run these numbers, you get this many square kilometers, great, right? Guys, how many digits of precision am I saying I have here? Like 4? We say 1, 2, 3, 4. Right. Now this here, maybe if I put a decimal point here, I'm claiming 5 digits of precision, but at least 4. Right? Do I really know that 7 is definitely a 7 though? You're right, I don't. Right? Because look at my inputs. How many digits of precision do I have even going in? Like this is like 2, like maybe 3, but kind of 2, right? Digits of precision. How about this 400 watt per square meter? It's like maybe 1 or 2 digits of precision. Maybe it's actually like 396 or something, right? Right. So however many digits of precision you have going in, if everything is multiplied and divided, that's all you have coming out of it. So the best I could say is maybe like 36,000 square kilometers, right? But anyway, that's just a kind of stuff. I'm not super picky about significant digits, but that's a good thing to think about, right? Right, you guys good day? Okay. Now, when you guys were walking in, you guys were solving some algebra problems. We did do some algebra last week, but I didn't get to like this level of tricky with you guys. So how many guys already solved this? T squared plus 4t is equal to 21, right? Who knows what t is equal to? Oh, yeah. What'd you get, Connor? 3. 3? You got 3? Right. Did anybody? Oh, yeah. What you got here? And also -7. Right. So Connor and Ashil are saying 3 and also -7. Ooh, so kind of like there's 2 solutions to this, because look at this. T squared. You have here. You have a t here. So what you're solving for, the variable you're solving for, it's being squared here. It's not being squared here, and also there's another constant thrown in the mix. What category of algebra problem is this? Starts with a Q. Quadratic. In fact, if you could scramble this around and say y equals and make it an equation, and you graph that equation, what shape would that take? Parabola, right? So, and however you solve this, I'll take you guys through 2 ways to solve this, but they both start out with the same step. What's the very first algebra step? Okay, you're saying factor? Okay. Now, right before you factor it, you first have to subtract the 21, or maybe there's a third way to this. I don't know. I'll show you guys 2 ways. Right? But they both start off with that step. Right? Get z equal to 0. Right? Okay, now you can factor. Sure, I like factor. Right? I'm going to write another term on here. FOIL, the acronym FOIL, which is really just a reverse process. I want to show you guys can go back and forth. Right? So let's do the factor. Right? So let's see. I'll put a t here and a t here. Okay? Now, what are 2 numbers that add to +4 but multiply to -21? +7 and -3, you're saying? Right? All right. Now, let's try this FOIL, because factoring goes from top to bottom. FOIL goes from this bottom step back to this top step. Let's make sure. FOIL. First, t times t, t squared. Outside, that's -3t. Inside is +7t. Add those together, you get 4t. Last, 7 by -3 is -21. All right, so we're good. So this and this are saying the same thing. They're just written differently. Okay? But the advantage of having it in this backward form is the fact that it's all equal to 0. And it's all multiplied. It's all multiplied equal to 0. Means that if this piece is 0 or if this piece is 0, the whole thing is 0. So I got t plus 7 equals 0. That could give you t is equal to -7. And if you go the other way, have t minus 3 is equal to 0. That gives you t is equal to positive 3, which is exactly the two solutions that you guys just told. You guys got that? Now, that's one way to solve this problem. What is the other way you also could have solved that problem? Okay, yeah. Box method, I'm sure that is a valid thing. I'm going to go a different way. But let's say there's a third way to solve that. How about that? What's the other way to solve it that Griffin might know? Diamond method. Man, you guys and your methods. Here's what I'm looking for. Here's the answer. Quadratic formula. I want quadratic formula. I'm sure you guys have all fancy ways of doing this. Here's what I'm looking for. So, look at that. Height is a function of time. Hey, if I throw something up and it's going to slow down and then come back down and speed up right, on the way down, do you guys think that its height as a function of time would actually follow a parabola shape? If you thought so, then you are right. Now, if you can somehow get the set equal to 0, right? Look at this. This parabola, there's two places it's equal to 0. It's like two solutions. Maybe like -3 and 7, for example. Right? Two solutions. If you set this up, plus or minus, hey, that's like setting up two solutions. If you ever set up the quadratic formula, you get one solution. Congratulations, you found the vertex. And if you get 0 solutions or imaginary solutions, it's like solving for something up here. Okay? All right, let's break this out real fast. So this is like, again, if it's like this quadratic form, if it's equal to 0, it's sort of like been predetermined. It's like been pre-solved for you. Break out the formula, you can make an equation with this. So in this version, it would look like this. T equals -b plus or minus the square root of b squared minus 4 times a. Oh, I guess there's an applied 1 right here, right? Times a times c. Don't forget this negative. That's all divided by 2a. Okay. Notice I extended my square root bar over that entire expression that's being square rooted. Right. Now I'm not going to do any more. I'm just going to stop right there. But plus or minus, there's two outcomes. And what are the two outcomes going to be? Boom, there you go. -7 and +3. There you go. There's a reason I picked t specifically, because in physics you see these all the time where t is like the independent variable sort of, right? Which usually stands for what in this class? Time, tick-tock. And if you ever come up with negative values for time, how can you interpret that physically? That means it's something that happened in the past, something happened in the past, right? Or could have happened in the past if you follow the model. If you extrapolate the model backwards. Right, you guys get there? Let's do another algebra trick here. So 1/2 mv squared equals mg8. Solve for v. Let me rewrite this here while you guys are writing that down. 1/2 mv squared is equal to mgh. Solve for v. Does anybody have it by now? All right, so let me give you guys a little time. So you can solve this. Who's gonna get it? Who's gonna solve for v? Solve for v. So this is like the same thing we were doing last week, except that it's variables instead of numbers, right? But it's the same like algebra type process. So you're going to get an answer that's in terms of variables. How about now? Anybody got now? Okay, so let's just start trying through this. And again, it's the exact same steps as we were doing with those basic algebra problems last week. If you need some more practice with those, I've got a bunch of algebra problems. This page is posted to Google Classroom. I just pulled 3 of them last week and we did those. Okay. So here, can I cross multiply the 2? So mv squared is equal to 2 mgh. Can I divide both sides by m? Is that okay? Divide m. Oh, what's going to cancel out on both sides? M. Goodbye. And the very last step is do what? Both sides. Square root. So V is the square root of 2GH. That is the answer, square root 2GH. Okay. Oh, no, I didn't just completely pull that out of the air. This actually has a physics story attached to it. I'll tell you guys the story. So you guys remember Galileo runs to the top of the Leaning Tower, starts throwing stuff off, freaking everybody out? You guys remember that? It's like, what is this? It's science. So let's go through these variables one by one. Say, what do you think they represent in physics? Now, M represents a lot of things, but as a variable, what does M stand for in physics? Mass, right? Hey, right here. I'll come back to that later. Right. What do you guys think V stands for? Velocity, lowercase v, velocity. Sometimes they'll say speed. Speed is like the magnitude of velocity. So something to do with like how fast it's going. Right? What do you guys think H stands for? Height, like a height change. Yeah, so as a unit, it could be hours, but as a variable, it's like height, maybe measured in meters. Okay. What do you guys think the G stands for? Gravity field. And so like Earth has a gravity field, maybe Mars has a different gravity field. Okay. So Galileo runs to the top of the tower, right? And he drops different objects. Now, this is actually a conservation of energy setup. The MGH is like an energy position, energy height, and the 1/2 mv squared is like an energy motion. Right? But it has to equate if it's a closed system, the whole bit. Right? So what this tells you is V, the crash speed, how fast are these things crashing onto the ground, is equal to square root 2GH, where H is the height of the tower, or the drop height, right? Could be the height of the Leaning Tower. Right? G is the gravity field of the planet. And look, the mass of these things didn't matter at all. And that's what he found in that experiment too. The mass can cancel out because they fall together. Right? How fast they crash? Square root 2GH. Just plug in the height of the tower, Earth's gravity, whatever units you have there. Right, guys get that? But now you have a general master equation that you can take anywhere. Right? So now Galileo is running all over town to finding towers of different heights. And he's dropping them different heights. Right? He's figure out the crash speed. Maybe he takes the whole Leaning Tower and puts it on the moon. Why not? You can change out the gravity field here and maybe get a different crash speed. Guys get that? So in this class, solving terms of variables like this, you guys see how it can be a really powerful method, right? You can just get universal answers to things. But we'll do this sometimes. We tend to do that more often in AP, with honors sometimes. With AP, a lot more often. With solving terms of variables. Let's solve one more in terms of variables here. Let's do mv squared on r is equal to mg. Solve for v. Actually, I'll walk you guys through this one. Okay. So same thing. It's just the same algebra steps from last week. Can I cross multiply this r? Yeah. mv squared is equal to mgr. Can I divide both sides by m? Divide m. Oh, does m cancel out again? M will always cancel out, but that's not too uncommon thing to happen in here. Can I take the square root of both sides? V is root gr. Right? Now, what's the story that could attach to this? Well, this is a dynamics type setup. mv squared over r represents centripetal force, so the force that would hold something in a circle. Mg represents the weight of something. I think I also put that on your variables map, right? So if this has a certain mass, like a certain inertia, right? And you have it in a gravity field, then there's some downward force on this right now, right? So mass times gravity field is equivalent to the downward force of the weight. Right? What's the centripetal force is only provided by the weight. That could be something in orbit, right? Like what's the orbital speed? It's more general form of that, but kind of same concept, right? Later on, a few weeks from now, I'll put some water in a cup and I'll have that cup on a string. I'll throw it in a vertical circle. Zoom, zoom, zoom. Right. Now, if the cup's going too slow, do you think when the cup is upside down, the water's going to fall out? Yeah, there's some minimum speed to get it around. What's that minimum speed? Well, if you know the radius of that circle, you know the gravity field of the planet. That's it right there. That's the answer. Right, so you guys will see that. Right, now these next two are really related to what I want to get to in the notes today. So let me just go ahead and flip over here. You know, we got kind of a tight schedule. We'll be able to fit everything in, but as long as we're keeping a pretty good pace. All right, so you guys still got your notes out, right? You guys still got your notes out? All right, so there are two categories of quantities that we're working with in this class, right? Called scalars and vectors. So you guys a little bit about each one of those. Right? If you want to see the definitions right now, I mean, you guys see it there on that slide anyway. I did type up the definitions and posted those to Google Classroom, so you guys have those there too. Okay? Now, some of the stuff might seem kind of trivial at first, but ends up being really critically important, especially the deeper we get into the class. Okay? So lots of numerical values in this class, like 3 something, right? But those numbers are always attached to units, right? You don't want naked numbers in this class. So like 3 meters. Okay, so maybe something to do with like distance, for example, right? Right, 3 meters. Right, so magnitude expresses a number and a unit to tell you like how to measure what you're trying to measure, right? Now, if that's all it has, like 3 meters, that's called a scalar quantity. There are a number of quantities in this class that are only scalars. For example, mass doesn't really have a direction associated with it, right? Like 3 kilograms. Energy values are scalar values. Like distance or speed are considered to be scalars. I just care about like magnitude, but I don't really care about direction so much. Okay? Now, if you do include the direction, sometimes the direction is specified, sometimes it's implied. Then you have a different kind of quantity called a vector quantity. And this is actually our main focus the rest of today, right? I'll flip it back and forth between the two, but I really, really, really care about vectors today. Okay, vectors. Okay? So vectors have not only magnitude, but also a direction. Right? So like 3 meters to the right. Right now we're not distance, but displacement. Right? A common vector in here is going to be a force vector. Right? If you push or pull on something, that's a force. Right? A common example I'm going to use is like kids kicking a soccer ball. Right? They aren't just kicking it with some amount of force, but also a certain direction there is to that force, and it's going to determine which way the soccer ball takes off. Right? You guys got scalars and vectors. Scalar is a magnitude and a unit. A vector is those things, but also a direction. Right? Sometimes the direction is implied, like in the forward direction or something. Right? Okay, let's do some examples here. We're just going to start off in one dimension. Let's say you walk 3 meters to the right, and then you turn around and walk 2 meters back. Right? Look at those 2 arrows. Those arrows you could call vectors, right? Vectors I'm going to draw as arrows. You guys see how they're connected tip to tail? Okay. Now, hopefully that's intuitive since we're talking about like walking back and forth, but other kinds of vectors, you can do the same process. The tail of one is connected to the tip of the other. Right? Now, 2 questions I have about this motion. 3 meters to the right, and then turn around and go back 2 meters to the left. First question, what total distance did you walk? 5 meters, right? Hey, is that like odometer in a car? The car odometer just adds everything up, right? That's called distance. That is like independent of direction. So that's like a scalar quantity. Distance is a scalar quantity. But I gotta ask a different question. Now, this is gonna seem kind of abstract right now, but it's gonna be more important the later we go on in this class, right? Look at where you started and where you ended. You guys see the starting point and the ending point? Let's say you go from the tail of the first vector to the tip of the last. What, how far is that? 1 meter. It's 1 meter to the right. And that's a different concept called displacement, right? Oh, do you guys see that pink vector that just popped up right there? There's a name for that vector. If you go from the tail of the first one to the tip of the very last one, it's called the resultant, okay? That's called the resultant vector, okay? So 1 meter displacement. Let me get rid of displacement and let's bring in kicking a soccer ball. Suppose there's two kids charging at a soccer ball. So you got a soccer ball in the middle of the field, 2 kids charging at it. And one kid kicks it with 3 newtons to the right. And the other kid kicks it 2 newtons to the left, but at the same time, so like smashing the soccer ball. Right? Which kid's gonna win? 3 newtons or 2 newtons? 3, but you see they're fighting each other, right? What is the net force on that soccer ball? 1 Newton. In this case, it would be to the right, 1 Newton to the right. You guys see that? Vectors. Right? So, okay, back to displacement, and then get these on here. So if you walk 3 to the right, to the left, then your displacement is 1 meter to the right, but your total distance walked is 5 meters, which is a scalar quantity. Okay, you guys got that? Vector, scalar, all good? All right. You guys ready to take this into 2 dimensions? 2 dimensions? Let's do it. What if you walk 3 meters east and then turn and walk 4 meters north? So, simple question. What total distance have you walked? 7 meters, odometer of a car. All right. Ready for this next one. If you look at the tail of the first vector and the tip of the last vector, and let's say you send it like as the crow flies, what displacement would that be? Huh? 5? Is she saying 5 meters? Who else is thinking 5 meters? How would you know it's 5 meters? All right. Pythagorean theorem, and it is a special right triangle. All right, you guys are all over this. You guys are stealing my notes. So 7 meters distance, but okay, right angle right there. We got, there's Pythagorean theorem, right? 3 squared plus 4 squared. Add that all up, take the square root, and you'll get 5. So that is 5 meters, and that is the displacement. Well, maybe I also need this angle here, right? Okay. So from beginning to end, I should have mentioned too, this is called a path independent. So you didn't have to walk 3 to the right and 4 up, or 3 east and 4 north, right? You could have walked any crazy path. It didn't matter. All you care about is starting point, ending point, right? As the crow flies. So the other question, though, to get displacement completely is, what angle is that at? What is this angle right here? Does anybody know how to extract that angle? What do you think, huh? Okay, so something to do with maybe a sine, something, right? Ooh, sounds like some kind of trigonometry, right? Huh. Does anybody know how to punch in their calculator and actually tell me what that number is? Maybe. I don't know. If you don't, that's okay. I just kind of curious if you did. All right, here's what we do. I'm going to flip my screen over and fill in these trig details with you guys. I have 2 trigonometry posters in this class. Right? One's the one I care about, but I'm going to delay that for a moment here. Right. Okay, so let's review this. Okay, so great. We got Pythagorean theorem. Now, Pythagorean theorem only works on right triangles. If it's not a right triangle, there's something called law of cosines, which is like a more generalized version of this, but I don't think you'll ever run into that in this class. Right? In any way, like any basic shape or a non-right triangle, you can break into smaller shapes until it does become right triangles. So you can still do that. Right? So a squared plus b squared is c squared. Okay, great. And the area of this blue triangle is 1/2 times base times height. If it is a right triangle, then very conveniently, the base and the height are the 2 legs. If it's not a right triangle, then you have to go about figuring out the altitude and all that. Okay, but you guys are good on this slide, right? Okay, now here's where here's where it gets a bit deeper. Okay. You guys remember like SOHCAHTOA? Right. Okay. All right. So I'm about to give you guys the updated physics version of that. You guys still taking notes, right? So, okay, I got a right triangle here. Only if you look really close, actually, this is a vector split into components. Okay? You guys see this hypotenuse labeled C is actually like an arrow, right? And you guys see these 2 legs labeled A and B are actually like dash arrows. Okay? Here's what I'm trying to get at. Suppose you walk like northeast. I might say like, well, how much north and how much east? You guys get that? And that's what the components A and B are. Well, B and A, right? Or I got a soccer ball. Here comes a kid. He kicks it with like 5 newtons, kind of to the northeast. How much north and how much east? You can quantify it. So now if you have like a bunch of kids, like, right, and they're all kicking all different directions, before you can solve which way does the soccer ball go, you got to break all those into components. So this could be like the first step of like a multi-step problem. You guys get that? So you guys might remember from math class the definitions of sine, cosine, and tangent. Okay, so as long as you have a right triangle, sine of this reference angle is defined as opposite over hypotenuse. So B over C in this case. Cosine of that reference angle is defined as adjacent over hypotenuse. And the tangent of that angle is defined as opposite over adjacent. B over A. Okay, you guys got that? Okay. Now that's straight from a math textbook. Right? Now, like 90% of the time in physics, the way you actually apply that is these guys right here. Right? Can we do a little algebra shuffle? Can you guys take this hypotenuse A and cross multiply it? And get B is C times sine of theta, and A is C times cosine theta, right? Those 2 right there. Here, see, like if you know like exactly how hard you're kicking the soccer ball and what angle you're kicking it, you can solve exactly like how hard to the north is going and how hard to the east is going. And then now you got like a bunch of kids and you can add them up, right? So that's like a later part of this problem, right? But these 2 boxes right here, B is equal to C sine theta, and so B is equal to C times sine theta, A is equal to C times cosine theta. Know these 2 boxes by heart because you're going to see this all over the place in this class. So many problems start with just like this is the first step. I see a poster up here like a cannon shooting a cannonball like up and to the right. How do you figure out where the cannonball lands? The first step is break the blast velocity into components. How fast is it going straight up? How fast is it going straight across the field? You could be moving around like some displacement. You could have kids kicking a soccer ball. You could have this is the first step. There's like so many problems. Okay, great. You guys got that? Know these 2 boxes by heart. It's just algebra shuffle away from the definitions of these things. Okay, but the question that actually made me flip over to this slide was how do you extract this angle? Okay, now if you look at sine, cosine, and theta, sine, cosine, and tangent. If you apply those in a calculator, so you can take sine of an angle, cosine of an angle, tangent of an angle, but you have to know where that angle is. But what if you only know the sides? Like maybe you know this is a 3, 4, 5 triangle, like 3, 4, 5 proportion triangle. But how do you extract an angle out of that? Well, you have to do an opposite process of taking a trig function, which is take an inverse trig function. And the example I showed you on this poster is inverse tan. Right? Now, if you're playing off tangent, it's something to do with the two legs, has nothing to do with hypotenuse. Right? You guys see that? Right? So I can do inverse tan of opposite over adjacent to tell me exactly what that angle is. Let's suppose this is a 3, 4, 5 right triangle. Right? What would I punch into my calculator to solve for this theta? Okay, yeah. So if you did 4 over 3, that would be referring to this angle up here, 4 over 3, which tells me this angle up here is 53 degrees. Or if I want to find this blue theta right here, I'll do inverse tan of 3 over 4. And that's telling me, well, I'll call it 37 degrees. Is that okay? That rounds to about 37 degrees, right? I need to ask you guys too. How do you access inverse tan? Look at that. It's not tan, it's tan minus 1. How do you get that on this calculator? Aha. So you hit second, and then you hit tan. Now it pops up inverse tan. Except there's another name for that. It's also called arctan. There's also arc sine and arc cosine. So like undoes the sine and the cosine. This gets undoing the tangent, right? Microsoft Excel likes to use that terminology. You type a tan, and then it'll take the inverse tan. Okay, you guys get there?
Yeah.
We're good. All right. Also for today, make sure your calculator is programmed in degrees and not radians. We might eventually use radians in here, but today we're doing degrees. All right, you guys good? That's good. All right, let's flip back over to this animation because there's some more things I want you guys to see. I had to point out some stuff there. All right, so who can tell me then? What is this angle right here? What's this angle right here? 53 degrees. Now you can get that by doing inverse tan of 4 over 3. You can also do inverse sine of 4 over 5. You can also do inverse cosine of 3 over 5. They'll all tell you 53 degrees. Okay? All right, there's 3 different ways to get it. Right. More often than not, I'll use the inverse tan one, but there you go. There's 3 different ways. Right. And, oh, look at that. Inverse tan of 4 over 3. Aha. Finally, you should be able to add vectors together in any order and still get the same outcome. So yeah, you could walk 3 meters east and 4 meters north and end up over here. Could you also walk 4 meters north followed by 3 meters east and end up at the exact same location, right? So I can add tip to tail red and followed by blue, or I can do blue followed by red, but that purple resultant didn't change. Right? What if you made this fancy? What if you got that going on? So suppose we're down here in the southwest, there's campsite A, and we got to get up here to the northeast to campsite B. But there's too many trees in the way. So we're going to go blue followed by red, followed by green, followed by yellow, right? Displacement vectors. They're all added tip to tail. That makes sense, right? And we're going to end up at campsite B there, right? But what if there's a different path through the forest and we followed the blue, red, green, and yellow, but in a different order, right? Now, what you're about to see, I'm going to hit play on this animation. And those vectors are going to slide around, but they're not going to change magnitude. They're not going to get longer or shorter. And they're also not going to change orientation. So they're not going to change their direction. Right, you guys ready for this? Look at that. Now they're tip to tail. Still, that purple resultant did not change. Right? That purple resultant is like as the crow flies. Let's see it again. Look at that. Now it's a different orientation. You can add them together in any order you like. Now that's a displacement example. But if those like 4 kids running on a soccer ball, like they're all about to kick that soccer ball with some force, those could all be force vectors. And that purple resultant could represent the direction that the soccer ball is going to take off with its net force. Right, you guys got that? Right. All right. All right. Questions so far? You guys doing good? All right, you guys got a page on your desk. Looks like this. Looks like bundles of fun. On one side is a table and 5 rectangles. You guys got a table and 5 rectangles? Right. Your table might be up here or down here. That was my fun copy adventure you guys want me to worry about. And on the back side, there are 10 trigonometry puzzles. Do you guys see a right triangle? Which, if you look really close, is actually a vector split into 2 dashed components. Ooh, look at that. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 puzzles. You guys see that? All right. Let's everybody do this. Write your name. Write your name. You guys write your name on your paper. Name. All right. Also write this. Write due Friday, 8:25. That was Friday, right? I think Friday, 8:25. Okay. Do Friday. Now, the side that we're looking at right now, I gave you a minimum amount of information that you could solve everything about the triangle. And since these are all vectors, look, they have vector type units. I mean, the angles are in degrees, of course. But what are these legs A, B, and or, X, Y, and Z? I made them X, Y, and Z. Well, I got meters per second. It's like a velocity. Got like newtons, could measure a force, like how hard are you pushing, kicking a soccer ball. Okay. Newton seconds is like that's like a momentum type unit, like impulse. Okay, so these are like vector quantities, right? And if you know a minimum amount about each of these triangles, you can figure out everything else. You guys get that? So they're all right triangles, so you're given the right angle. And some of these, I gave you guys the angles, or some of the angles, and maybe one of the sides, right? This very last one, I didn't give you angles at all. Ooh, you have to do some kind of inverse trig function to figure those out. You guys think you do that? Right? You guys think you can navigate those probably? Right? You're there? Right? Well, I'll give you guys a little time in class tomorrow to do this too. But the rest of the time in class today, ooh, am I doing good time? I don't think I forgot anything. All right. Let's flip over to the front side. This front side is the laboratory version of this trigonometry. Right? So there's all the textbook theory you learn about sine and cosine and blah, blah, blah. Right? But science is empiricism. So you guys have two measuring tools. You guys got a ruler and a protractor. I'm going to walk you guys through at least one of these triangles today. Right, I'm going to pick the Schrodinger triangle. Now this table, you guys see it has 5 rows? 5 rows? Right. One of them is Schrodinger. I'm going to start that one because I'll walk you guys through that. You guys pick 3 triangles, 3 of your favorites. Let's say I like Heisenberg and I like Tesla. How about that? I got Heisenberg, Schrodinger, and Tesla. Star any 3 of those and just ignore the other 2. I'm just going to have you guys do 3. Can you guys pick any 3? You guys have 3 rows starred, right? You guys got 3 triangles picked out. Now going across, ooh, there's a bunch of columns. Now some of these columns say measure, and some of them say calculate. You guys see that? Measure and calculate. Hold on to the idea. This is going to come back here in a minute. Right? So the first 2 columns say alpha and beta measured in degrees. It's protractor time. We're going to grab what is the angle, like how big is this wedge? What is this angle alpha? That's my first measurement. Okay, one way I can get this, protractor. Guess how I use a protractor? I'm going to take this node of the protractor right here in the middle. I'm going to park it right on this corner. I'm going to zero out this leg. And the hypotenuse crosses exactly through the angle. Ooh, except there's 2 numbers it crosses through. It crosses through 13 degrees, and it crosses through 167 degrees. Which one of those angles is correct for alpha? But yeah, 13. Yeah, 13. Because it's definitely small, right? 13 degrees, I'm putting under Schrodinger. Alpha is 13 degrees. That is a 13-degree angle right there. Okay? Guys, every one of these triangles I gave you is a right triangle. Maybe I should have drawn a right angle for one of these, right? Which means the right angle is going to be the largest angle in a right triangle. So are alpha or beta going to ever be more than 90 degrees on this paper? No, they're all going to be less than 90 degrees. You guys get that? Okay. Now, the other way you could have measured alpha is you could turn this whole thing upside down. Go this way. You still park the node of the protractor on this corner. You zero out the hypotenuse in this case, and you see what it sweeps through. I'm going to purposely fudge this just a little bit. There's a certain point I'm trying to make here. Right. Suppose I measured it like that. And then I'm looking at, that looks like, what would that? Oh, but whoops, sorry, I'm getting ahead of myself. Never mind. All right, so if I do it properly, that's still 13 degrees. Okay, so it's still 13 degrees. Okay, all right, so it's 13 degrees either way. You guys got it? Okay. All right, let's go grab beta, the other non-right angle. Okay. I'll give you guys a little trick here. Some of these triangles are kind of small, and some of these protractors are kind of big, which might create a little bit of a conundrum. So what you can do, what's going to solve that, is you can extend one of the legs, or maybe 2 legs. See how I just extended that leg? So that would make it easier to measure that angle. You guys see that? Right? You don't have to do that. Maybe I don't have to do that on this particular triangle, but you could do that, right? I'm still going to take the node, park it right on that corner. I'm going to zero out that leg and see what does this cross through. Okay, here's the one I was going to intentionally fudge just a little bit, just make a certain point. Right? Suppose I measure it like this, which isn't exactly right, but it's pretty close. I get, that looks like 78 degrees. So I'm going to go to my paper. under beta, I'm going to write 78 degrees. Right. Now pause here for a moment. What do you guys know about angles in a triangle? All three angles in a flat triangle should add up to what? 180 degrees, right? Now 90 of those degrees are already taken up by this right angle, which means that ideally alpha and beta should add up to what? The other 90 degrees, right? Now let's check out my two angles, 13 and 70. Oh no, those add up to 91 degrees. Okay, so what should we do? Here's a couple options. Option A is I can scratch out the 78 or erase it and write 77 because that's what the math textbook says it should be. Option B is I can say, no, that is my empirically measured value. I'm going to leave it like that, and it's just going to have to add up to 91 degrees. Show of hands. How many guys think that you're going to erase the 78 and write 77 because that's what your math teacher told you? How many guys think you're going to leave the 78 because that's your empirically measured value? Aha, there's my scientist right there. There's my scientist. So what you should actually do depends on what class you're in. Guys, if you're in a math class, if you're over in a math class, should alpha and beta, should you make sure that they add up to 90? Yeah, great. But we're not in a math class. We're in a science class. And your empirical measurements are more important than textbook theory, which means I'm going to go with, now maybe you want to measure like 3 times and like take an average or something. But it's more important to go with your measured values. I will show you guys why. Is there any exception to the rule of all the angles in a triangle should add up to 180 degrees? Is there an exception to that? What? All right, got a winner. How about if you're on a non-flat surface? Okay, here's the Earth. What if you put 1 point on the North Pole, 1 point down here on the equator, 1 point way over here on this part of the equator? Oh, look at that. It's a triangle shape where those angles add up to more than 180. Right? Like 270 maybe in that case, right? So if you were out in the world doing some experiment and your angles aren't adding up to 180 like the math textbook says they should, it might be telling you something about maybe the surface that you're on. Maybe that's actually revealing somehow. And so it's a science philosophy rather than math philosophy, right? All right, what's we got? Next cell, measure side C. Guys, are we using inches or centimeters? Centimeters. All right, you guys are on. I'm looking at 11 point, I don't know, what's that? 11.8 maybe? 11.7, I don't know. I'll call it 11.7 centimeters. It's either that or 11.8, can't tell. Okay. Next measurement, side A. So my empirically measured value of side A is going to be, I'll call it 2.6 centimeters. 2.6 centimeters. All right. Now skip a few cells because there's one more measurement. I put it way over here. You guys will see why in a minute if you don't see it. Right. Side B, I put way over here. You see that? Measure side B. Okay. Let's grab side B. Side B. All right. I'm getting for Schrodinger. What would that be? I think it's like 11.4 comes pretty close to. I'll call it 11.4 centimeters. There we go. Okay. Those are my 5 measured values for that triangle. Say we're given the right angle, right? So the other 2 angles, alpha, beta, and the 3 sides. Right, you guys got that? Okay. Now, these other cells, these 3 here and these 3 here, see how they say calculate, right? So that's going to be the calculation approach. Can we also get those sides from a sine or cosine method or from, well, some do it the square root I'll get to later, right? We'll tell you sort of a real world application of this. Suppose we're going to have a project. We're going to tunnel through a mountain and we're going to lay some railroad track, right? But before we start this project, we got to know how much track is going to be. How long is that tunnel going to be, right? Well, we can't measure it because the mountain's still there, right? There's too much dirt in the way. But we can calculate it, right? We can measure all around the mountain. We can calculate how long it's going to be, right? So we can approach these things from different points of view. C times sine alpha. Well, if you have C and you multiply by sine of this angle alpha, and it's stated here, but right, won't that give you the opposite side right here? Right, so let's do that. Let's go 11.7 times sine 13 degrees. That's telling me 2.63 centimeters. C times cosine of beta. Right, so now we're up, now we're playing off the other angle. But guys, if you start with the hypotenuse, multiply by cosine of this angle beta, that's like switching over to adjacent to the angle beta, which also tells you the same side right here. Right, so it's the same side. So what is 11.7 centimeters times cosine of 78 degrees? 2.43. That's off a little bit, but it's close enough. Remember, I purposely fudged that angle so I can make that full point about. And finally, what is this whole deal about square root of c squared minus b squared? Do you guys know where that's coming from? The what theorem? Pythagorean. Here's Pythagorean theorem. A squared plus b squared is c squared. But what if you're solving for a? Subtract over b squared, take the square root. Hey, that's exactly what that says to do. Right? A is the square root of c squared minus b squared. Let's do that. So square root of 11.7 squared minus 11.4 squared. That's 2.63. So that's like backward Pythagorean theorem. By the way, if you're getting like negative numbers or wacky numbers for any of these, make sure your calculator's in degrees, not radians. That's a common thing. Right? If this is showing up error, make sure you're not confusing A and alpha. A and alpha are two totally different concepts, right? All right, let's finish off this row. C sine beta. C times sine beta will flip over and tell you something about side B. So 11.7 centimeters sine 78 degrees is 11.44 centimeters. C times cosine of alpha. C times cosine of alpha, that also tells you side B. Let's see if it does. 11.7 centimeters cosine of 13 degrees is 11.40 centimeters. And finally, reverse Pythagorean theorem, c squared minus a squared should also tell the square root of that, right? Square root of c squared minus a squared should also tell you b. Square root of 11.7 squared minus 2.6 squared. That's 11.41. All right. Oh, just in time. There's the bell. All right, you guys have a great afternoon. Bring your laptops tomorrow. We'll work on this page a little bit more tomorrow in class. And yeah, more physics adventures.